see us?
I forgot to hit the start streaming button on YouTube. I'll be darned.
So let me need to redo our intros.
I have to do all this all over again.
Yeah.
All right, that's fine. I just started streaming. Sorry. All right, let me go back. Sorry, guys. We got to do this again. I was live on the other things, but I forgot to do it on...
It worked great in rehearsal, you know.
Okay, yeah. All right, here we are. We're back. Now our audio is still live. Good. Thanks for pointing that out. All right.
Yeah. Now I'm showing the, now I see the card.
Do you see it now? Are we streaming on YouTube?
Right. No.
We're not streaming on YouTube.
Well, you're past the wait, but I've got the DKIST card up instead. I don't have
well, that may be because that's what I'm showing. Now
that's fine. Then you're good.
Now you should be seeing us. All right. For those of you who on Twitch and Twitter and Facebook, you're seeing this a second time. Good news, everyone. It's time for Telescope Talk Pro, our bi-weekly Hangout/live discussion where we highlight the amazing astronomical discoveries as well as all the cool equipment being built on ground-based observatories around the world. Today, we're talking about the Daniel K. Inouye Solar Telescope, or DKIST, that is under construction at the Haleakala Observatory on Maui. It is named after a U.S. Senator from Hawaii, and it has and before that, it was also called the Advanced Technology Solar Telescope, and they changed the name in 2013, I believe, and it has a planned completion date of next year, sometime in 2019, and we'll find out more on that here in a bit. It's expected to become the world's largest solar telescope, and it will have a whopping 4-meter diameter aperture mirror, and it is funded by the National Science Foundation, and it's managed by the National Solar Observatory. So keep that National Solar Observatory part in your head for I'm going to ask you a question in just a minute. Before I get started, let me just say that we pride ourselves here at Deep Astronomy World Headquarters on bringing you access to professional astronomers from around the world so you can interact with them directly. If you're watching live on YouTube, Facebook, Twitter, or Twitch, please leave your questions and comments on the live chat. You guys already did that, said there's no stream here, as well as our Discord server. I'm also looking at that. The link to that is in the description box, so please make use of that. And if you're watching this, of course, as the stream after the fact, or as a VOD, or if you're listening to the podcast version of the discussion, you can get access to all the visuals that we show here. I have a Google Drive folder all set up if you want to download the visuals for your own personal amusement. And I also invite you to comment and thumbs up on our Humble Hangouts because we want to spread the word about these resources for other people. So please help us out by doing thumbs up and all that kind of stuff. So let me start by introducing my co-host. His name is Christian Ready from LAUNCHPAD Astronomy. He has a YouTube channel as well as I do, and he's producing some really good astronomy content. So you need to check him out. Go to the link in the description box to subscribe to him and watch his stuff. So welcome, Christian. It's good to have you here.
Tony, good to be here. Good to be back. And thank you all for joining us today on Telescope Talk Pro Live.
Right. Thank you.
In HD.
Well, hopefully it's in HD. Hopefully it's even streaming. We'll have to see about that.
Sorry about the technical hiccups for everybody, but I think we got us all good to go.
I only have like a million buttons to push. So, you know.
Tony, you are just a one-man production machine. I love it.
Yeah, like a robot.
We are charging ahead. No fear.
Where's Ray Kurzweil when I need him? Okay, quick fun note. If you're watching this stream on Facebook, I was setting this up and I happened to find a way that I could put up trivia questions. I hope it's working. I don't know if it is, but I put a trivia question on this stream. So listen to this, and then I'm going to give you the answer at the end of the Hangout. And this has to do with the National Solar Observatory, which is managing DKIST, but it used to be located at Sunspot, New Mexico. It's also now in Boulder, Colorado. What is the significance? Here's my question. What is the solar significance of the main highway leading to Sunspot, New Mexico, which is the site of the old National Solar Observatory? Option 1, its length is equal to the solar diameter. The length of the highway is equal to the solar diameter. Option 2, when you drive on it during either solstice, the sun is directly in your eyes. Option 3, the highway is named after the wavelength of the hydrogen alpha line. Option 4, the Air Force decided to build the road there in the 40s so they could easily see the atom bomb testing and found that they could also see the sun pretty good from up there. So which one is it? I'll give you the correct answer at the end of the Hangout. The highway leading to the National Solar Observatory, the old one, in Sunspot, New Mexico, has the name of that highway has solar significance. What is it?
Right.
Okay. Our guest today
What's
are
the
people.
prize? What's the prize?
Oh, I don't have a prize.
We don't participate.
It's
You get my undying
of knowledge.
admiration, folks. That's what you get. I don't even know if the thing's gonna work. I set it up on Facebook, and I don't even know if it's up now. So people let me know. Okay, so you get my undying admiration. That's the prize.
Undying,
and that's important because
undying.
Admiration can die. So my guests today are people you've seen before when they were wearing their Planet's Foundation hats. You may remember them from when we were doing the ExoLife Hangouts, which you guys seem to really enjoy. But you may not know that they are also solar physicists working on the DKIST team. So we have Dr. Jeffrey Kuhn from the University of Hawaii, and he is a co-I on the project. He's in the lower right panel there. And Dr. Svetlana Berdughina, she is the director of the Keupenheuer Institute in Germany, a big collaborator on the DKIST. And she's also an extraplanetary and biology researcher. So welcome, guys. It's good to see you guys here. I'm glad to have you guys back. You guys are fun to have hangouts with. How you doing?
Thank you. Thank you for having us. And in this second hat that we have solar physics. That's also very exciting.
Okay. All right. So let's start with somebody give us an overview of the Solar Observatory, where it's being built, and when it's going to be completed. Jeff, you want to do that for us?
Sure.
And while you're talking, I'm going to have this illustration up that's got all these labels of the observatory and what it's got. So while you're talking.
Well, so it's this would make an interesting trivia question too. When did the germ of the idea for the solar telescope get planted in the minds of solar physicists?
Of this telescope or any solar telescope?
Of this one. And you might remember some of these people. Did you know Ray Smart or Serge Kuchmy?
Oh yeah, Ray Smart. I did not the other one.
Yeah, well, so really, those two guys were some of the first. This was back in the 70s. The first scientists to point out this idea that you could build a telescope that is an off-axis telescope that has just a mirror without a hole in it, like most astronomical mirrors, and create a telescope that has really exquisite performance for seeing, say, the corona, the outer part of the sun. And that goes back to the 70s. So a lot of the ideas for this telescope have been hanging around for about 50 years. The proposal to build this telescope goes back, it goes back almost 15 years into the National Science Foundation. And it's taken that long to just get everything together. Hanging around for the basic construction started about 5 years ago, 6 years ago. And like you say, it should be finished at the end of this year, but probably first light and the first scientific results from it won't happen until 2020. And it really is a big deal. It's the biggest jump in humankind's ability to see the sun since Galileo, I would say. And Galileo took us from looking at the sun with our eyeball to looking at the sun with a small telescope. And the jump in our ability to collect information from the sun with this huge 4-meter diameter mirror is an enormous advancement. It's more than an order of magnitude from anything up until this point in time. So it's a big deal, and it should be online and ready to create new information for us in I would say in the middle part of 2020.
Okay, so where would you say the construction is roughly at this point? I mean, I've got a picture up of the mountain leading up to Haleakala, and it's got cranes and stuff there.
How do I see the picture that you've got?
Well, I tried to. So in the you need to go to the Google Drive folder and just click on. Unfortunately, I can't show you when I'm broadcasting. So if you just I'm showing the one right now called. Well, I can't see the whole thing now. It's called 2016-01-12A. It shows the construction site.
Yeah.
And
so
yeah,
I got it.
I
got it.
Yeah, that's what I'm showing right now.
Beyond that, so that big crane was the biggest crane on Maui in years, and it's gone back to Los Angeles. All of the external construction is done. I think you had a picture of the primary mirror even, right?
I do, yeah. It's I've got that up now. It's what is it, M1 Coding group photo.
Yeah, and that is a really cool picture because this astronomical mirror is, believe it or not, the aspect ratio, the ratio of the diameter to the thickness, is bigger than any other telescope that we're aware of. There's some space projects that have been thinner mirrors, but that look how thin that mirror is.
Yeah.
Compared to the diameter. It's really, I mean, in some ways, the mirror is the new technology. And the other amazing fact about that mirror is there's no hole in the middle of it.
Yeah, why is that?
Yeah, so I was going to ask that as well. You mentioned earlier that not having a hole in the mirror increases the performance, and I can imagine that just because, okay, we're not blocking some of the light and cutting a donut hole, but to what level does that really raise the performance?
You're exactly right, Christian. That when you don't have any optics sitting in front of the mirror, it's not just the hole, but it's those thin supports that support.
Right.
Call it the spider in a telescope, right? That, you know, in pictures of stars in almost all telescopes, you see the star-like pattern, the bright star in a photograph, and then you see the rays, and those are created by the diffraction of the telescope. That is the structure in front of the mirror, and this is the first telescope of its size that doesn't have that. There isn't any of that diffraction.
Wow.
And in a telescope which is, so this telescope is called an altitude azimuth mounting. What it means is that it has a vertical axis and then it has a horizontal axis to point anywhere in the sky. But what that means is that as the telescope tracks the sun or a star or whatever, another star, the object rotates. And that's a problem in a telescope which isn't off axis, because those diffraction spikes rotate through the field and they basically cover most of the field of view.
Oh, okay.
Yeah, but you still have to worry about field rotation when you.
Well, yeah. No, the field rotation is there, but you just don't have to worry about this thing that's orders of magnitude brighter running through your field of view. So when we look at the corona, we have only the area diffraction of the aperture. We don't have all the other mess created by the secondary structure.
Okay.
So it has a lot of other optical and optomechanical advantages when we don't mount something on front of the mirror, and some of them you can imagine. But the big thing is that this telescope for the first time is going to be able to look at the faint part of the corona to be able to see, well, as solar physicists in astronomy, astronomers worry about a dark energy or a dark matter problem, right? Something that permeates space and controls how things happen, but we can't measure it. That's the dark matter. That's the concept of the dark matter. In the solar corona, there's a dark energy, and we actually know what that dark energy is. There's a quiz for you. What is the dark energy in the corona?
I have no idea what you're talking about. What are you talking about? Dark energy in the solar corona?
The
Well,
universe
it's anything
of the
what we
corona?
don't understand. We call
Dark energy just means
dark
it's something we
energy.
can't measure. We haven't been able to measure, right?
So let me guess. Your dark energy for the corona is that which makes the corona get really hot.
Yeah. And we know it's related to the magnetism. So the dark energy in the corona is the magnetism. And guess what, guys? We haven't been able to measure it except in a couple of isolated experiments. This telescope is going to reveal the dark energy that makes the corona hot and expand into space and connect with the Earth. And that's another reason why it's a big deal. It's another reason why it's designed in this unusual way, where there's no obstruction of the pupil.
What wavelengths are we talking about here, Jeff?
Well, because it doesn't have a lens, the only thing that limits the wavelength are the coatings on the mirror and the atmosphere. And it's up at 10,000 feet, and so we don't have as much atmosphere as you would somewhere else. So it's going to go out into the far infrared, and if it weren't for the coatings, it would go bluer than, well, so you astronomers know that we can't really see much below 3,900 angstroms. But actually on Haleakala, because there's a whole lot less atmosphere, we could go even bluer than that, down to say 3,800, which turns out to be not so much, but actually has some other advantages. I don't know, Svetlana, you want to add to what I'm saying?
Yeah, I would like to add that it's a big deal, what Jeff said for the corona, but another big deal is that this is maybe first time, truly multi-wavelength observations of entire solar corona at the same time. The possibility is open because we in solar physics, we were on ground based, mainly focused on studying the photosphere, that surface we see like a yellow surface by eye. But there is this hot chromosphere above it and hot corona. So chromosphere is between 10,000, 100,000 Kelvin, and corona is a million Kelvin degree. And then that was usually observed from the space. So, and now DKIST will allow us to see all these layers, three layers, what we out atmosphere call photosphere, chromosphere, and corona, at the same time and in different wavelengths and in polarized light. So this is, from my point of view, it's the first truly hyperspectral polarimetric imager. So it's like 4D imager, it's truly first time. Because in solar physics, if you talk about telescope on these programs, you compare solar approach with stellar, there is a difference. When we look at stars, we don't resolve the stars, so we give up on imaging, but we can gain a lot in the spectral domain. So we get like entire optical spectrum, all spectral lines. In solar physics, since we're also having dimension in imaging, often it's very difficult to have entire spectral domain. So most of the science is focused on very few lines, and when you do observations, it's one or two lines.
Yeah, but Svetlana, the reason for that isn't it usually the atmosphere gets in the way? I mean, even in Haleakala, it's gonna. Well, sure, because you can't.
No, not at all. I mean, I talk about optical spectrum, say from 400 nanometers to near infrared, like 5 microns. We can get everything on the, well, practically. I mean, like it's again ranges of wavelengths, but this time, for the first time, we can get up to 10 spectral regions observed simultaneously and form a different layers in the solar atmosphere. So we can look really, truly three-dimensional structure of this atmosphere. Plus, because the telescope is so big, we can do it with high observational frequency, means that high cadence, what we call in time. So it will be like a truly dynamic structure of 3D dynamic structure of the atmosphere that we can study. So that is also very unique to this telescope.
Before we get too much further, hang on, Christian. Let me just get to this, and I'll let you talk.
Okay.
I want to Upcycle Electronics has got a clarification that he needs. In layman's terms, what is the difference between the total optic system that allows the mirror to lose the whole? Is it reflecting off axis? Yes, this is an off axis system. I wish I had a diagram or a schematic of what that would look like, but I don't.
I think there is one, Tony.
Your pictures.
Where is it?
You can show the frame of the telescope. It shows the
yeah, well,
geometry.
okay, I've got it up now.
Yeah, you can.
Oh, so at the very top, I really can't see the off-axis-ness of it, but I guess so light reflects off of that M2, which has also got a heat stop on it, and then it goes down to the mirror, but not, it reflects it, but it's not sitting in the center of the mirror, right, Jeff? Is that
let me see if I can, I might be able to share a screen if I can find it.
Oh, don't do that. No. It'll ruin my Hangout. Unfortunately, I've lost that ability too.
All right.
So unfortunately, yeah. So to keep everybody in frame.
Jeff, you can have a picture in your office and you can show it on your video.
Yeah, but Tony, which picture are you looking at right now?
Well, I was looking at the image called obslabel.jpg. It's the 20. It's got all the labels on it. With of the telescope levels, the Kuhn level.
Look at your picture of the structure in the telescope dome.
Okay, which one?
That's it's
2017, 12, 13.
Yeah,
I got it.
Cut away.
Well, it's not. It doesn't have the labels on it, but it has the an actual photograph of it.
Yeah. I think I've got it up. It's called tmamove.png.
Yeah. So this is really exciting because they're now. So the primary mirror is now in the telescope, and it's sitting. So to the right, there's a sort of a gray box that you see, which is not the primary mirror. This was taken when there was just a counterweight. But that is where that ultra thin mirror sits in a very complicated control cell. And so the light basically comes in straight down, hits that mirror, and then goes off to the side. Towards the upper left, you see kind of a white box structure. Mm-hmm. And that's where the secondary mirror is, completely off to the side. And what it does is then redirect light back down towards, you see at the bottom of the picture, there's an open hole and basically that's the elevation rotation axis.
Okay.
It brings the light back down to that rotation axis, and then it goes down. And we got to look at your other cutaway picture to see where the light goes. But this is, I mean, who would look at this and say that looks like a telescope?
Yeah, I see what you mean now. The primary is completely exposed. There's nothing in the way.
Absolutely. Right.
Yeah, and I see what you mean now. So wow.
And just to further clarify the image, on the very edge at the top of the primary mirror cell, that black, that folded up thing, I guess that's like a mirror cover. Is that what that is? That's retracted?
You know, I don't think the primary mirror is actually in there yet.
Oh no, but what I'm saying is that black folded structure that's at the top of the primary mirror cell. I'm assuming that's like a mirror cover.
That's how it works.
Okay, yeah. So I'm because it's helping me to imagine the mirror sitting there. So you're saying that right now the mirror is in fact installed. Just that in this photograph it wasn't installed yet. So that's just a counterweight.
Yeah.
Okay. Cool.
And if you want to look at the cutaway image, let's see, which one is that?
You mean it's called labels? It's got the labels on it.
Oh yeah. So, all right. So you see the blue structure at the top. That's what we were just looking at, which is actually built now and in place.
Okay.
And you can see the yellow rays of sunlight coming straight down.
Okay.
They hit the primary mirror and they go off up to the diagonally up and to the right.
Okay, like that purple box. It looks like it's colored in purple, I guess.
Yeah. And then the light makes its way all the way down. So you see it's labeled Coude level, COUDADE.
Oh, okay. So that's about like a third of the way from the ground.
Yeah, and there's a big merry-go-round there.
Okay.
Which is, I don't know, what is it? You remember, I think it's like 15 or 20 meters across. And the instruments are all down on that Coude. And that whole thing rotates as the telescope tracks the sun.
Oh, okay. So am I seeing, I mean, maybe I'm just imagining it, but at the Coude level, is that supposed to be like a human figure standing in there for scale?
That is indeed. There is
okay.
Jane Observer working right there.
Jane Observer. Okay. So she's standing amid all of these instruments.
Yeah.
That are arranged on the Coude platform.
Yeah, somehow.
Yeah.
All 5 instruments, first light instruments, will be on this platform. And what is amazing is that 4 of them can be combined and observe the sun at the same time. So and in the near future, I believe the 5th one also will join. So all 5, in principle, could be used at the same time.
Wow, simultaneous imaging or simultaneous sensitivities is really
yes, in different wavelengths. It's usually and different.
Yeah, my instrument is the odd one out because it's very far in the infrared and it doesn't play well with the others.
Oh,
but there is hope. It's not completely hopeless. There is hope that it can be added later. It's just on the first light it won't be, but later it will be.
What wavelength? What wavelength
all of
is
the
yours?
Cool instruments can work together, and then maybe they'll let Jeff play.
No. When we play, we get the whole telescope to ourselves.
Yes, exactly. Exclusively, he gets the telescope exclusively.
I did have a question, Svetlana. I just kind of wanted to circle back to something you mentioned earlier. You talked about the fact that this is going to be for the first time we're going to have polarimetry or polarized image.
Polarized polarimetry in many wavelengths, many spectral lines.
And I was wondering if you could just clarify for us, what that means and what the benefit of that is. Yeah,
so polarimetry is used to detect magnetic fields. That's first time was done by I kind of have hard time to say when was polarimetry used first time, but first time magnetic field was measured on the sun in 1908 using the similar technique that's called Zeeman effect. And
that was Mount Wilson, right?
Hall. Wasn't it Mount Wilson or?
Wasn't it Mount Wilson? Tony might remember.
Hale, Hale did it. Yeah.
No.
George Hale. And so it was celebrated 2008, 100 years discovered magnetic fields, because you see, Jeff said Galileo discovered sunspots, but only 300 years later we learned that they are magnetic.
Mm-hmm.
So now 100 years later we kind of find out that actually they're not just black and solid, they have extremely fine structure, and that's what we will study with this telescope. So what polarimetry does is that the light which goes through the solar atmosphere, and if there is magnetic field, then it's kind of behaves in different way, that some waves start to oscillate this way, some start to oscillate this way, and some go this way and this way. What's called linear and circular polarization. So that magnetic field perturbs the photons, oscillation of electromagnetic waves. And that's what we use equipment to, like filters, basically one can call them, to measure all these states separately. We measure state like this, and state like this, and state like this. And one can understand it in lay terms using the polarized sunglasses, when you go outside and on skiing slope, or you go on a water boat trip, you put polarized sunglasses, so because the glare from the sun is so blinding, you want to cut off this glare. And what we do in astronomy, we actually want this glare. That glare contains information about the surface which is scattering this light. But if you have magnetic field, it's even more complicated. So that's kind of the way. And one can experiment with it. If you have the polarized sunglasses, you put them this way and you see one picture. But if you do it this way, you see the other picture. You see this glare coming in and out. And you can do the same when you go to 3D movie. You have also these polarized glasses. You can do like this, and then you see that actually it's changing. So that's polarization.
Yeah, it always makes me seasick when I tilt my head in a 3D movie. But yeah. So let me get a couple questions in. John Suffel wants to know about the diameter of the mirror. It's 4 meters. And Larry Keese is asking, how will this scope work with the Parker Solar Probe? Now we know that
it's actually 4.2 meters.
Okay, 4.2 meters. And Parker Solar Probe, guys, is it gonna like steal your thunder with this dark energy business, or it's going to fly to the sun, Jeff? That's going to be pretty hard to beat. I mean, it's going to go out there and touch it. That's what NASA says. It's going to touch it. It's going to poke it.
In situ measurements, yes.
Yes.
That's a different.
And is it going to get your dark energy scooped?
Well, the Parker Solar Probe is going to sample the corona.
And the
but
magnetic
the point
fields,
of being able to stand back is like it's the difference between a close-up microscopic picture versus a family portrait. And the DKIST, while it doesn't see the whole sun at once, what DKIST does for us is give us the big picture and shows how things are interconnected. And that interconnectivity is something that it's a little harder to get. So what's magic about Parker Solar Probe? It's like what you said, we're going to touch the corona, but we're not going to touch it all the way up to the surface, and we're just going to do things like measure the constituents in the corona. So they're really different, and they're complementary, and people are already gearing up to be able to extend what PSP does for us by combining simultaneous observations with DKIST.
Cool. Well, let me just ask a follow-up question from Larry. From Adams Energy, who he wants to know about the resolution of the telescope, and you just said that it's not going to see the whole sun at once. So that tells me it's got a narrow field of view as well.
So let's see. So the instrument with the biggest field of view is this one that doesn't observe simultaneously with the other instruments.
Your instrument.
That's my instrument, and that will see. In astronomers' terms, that will see 5 arc minutes, and 5 arc minutes is 300 arc seconds, and so it sees. So the diameter of the sun is 30 arc minutes, so it sees about 1/6 of the diameter of the sun at one time. Now, the mirror is huge, right? The mirror by solar standards, and so the smallest detail that it can see gets down to about the size of 100 kilometers. I mean, that's another one of the great.
Oh, in corona, it depends on the wavelength. Yeah. So the smallest what we can see in the optical is about 20 kilometers, and that's very exciting.
Wow.
Because now we can see only 170 kilometers. So this will be like 3 times better if you go to shorter wavelengths. It's really exciting.
Yeah, and that's in a smaller field of views.
Yes. Of course, I mean, it's like you take a microscope and you look at a big thing, you see the tiny patch of it. That's the same with the sun. You take a big telescope and we see a smaller part of it, but with much higher resolution. So it's sometimes I say it's microscopic solar physics, what we can do.
So this is a personal question. We're having worked on the Mauna Loa Solar Observatory for many years. One of the things it has done, and is that no other ground-based telescope has managed to do, is that it used to have a Mark IV coronagraph that measured polarized light. It would scan. It was a linear CCD. It was just one row of pixels, and it would scan the entire area around the disk of the sun to get a low resolution, I'll give you that view, but you could see the solar corona in white light every single day, and that was a very valuable, I thought, data set, one of the first I ever worked with. Will there be any kind of analogous data coming off of DKIST, something that actually images the solar corona in the same way?
Well, that is a very prescient question that you're asking, because just this week, there's a meeting of scientists in Boulder, one of our favorite places for studying this, which has convened a whole bunch of people to talk about exactly this question of what are the long-term sort of large-scale solar observations that we should be taking, like the Mauna Loa data set that ran for years. So DKIST is more of a microscope. It's run by, all right, you submit a proposal. I want to attack this problem. Why is it that sunspots lead to flares occasionally? And so you got to go off and you got to do detailed studies associated with that question. Lots of questions we didn't know how to answer when you started the Mauna Loa data set. And the value was the long-term, very homogeneous set of observations that scientists continue to use that data for. DKIST will have that through dedicated long-term observing, and they'll still be more microscopic, but it's possible that we'll be able to do something like Mauna Loa that sees the whole corona by just taking a bunch of observations with cryo-NIRS. That's this instrument we've been talking about. All the way around the edge of the sun, but it won't see out as far as Mauna Loa does, and it will be seeing other things. It won't be taking. It's not so much the imagery that's so good with that data, but it'll be the spectroscopy and the polarimetry that we get. And my expectation is that yep, we're gonna have something like Mauna Loa, but it's gonna be a microscopic image, and it's gonna happen every day.
By microscopic, you mean higher resolution?
Higher resolution.
Small spatial resolution.
Yeah.
Yes,
okay. But it doesn't.
Less than 100 kilometers. Yeah.
Right.
Okay. So based on what I just heard you say, then the mode of, which leads to another question. The mode of operation is you're going to have to apply for time, make a proposal, and you'll do the observations. But this won't be synoptic, will it? This won't be a survey. Like no, I couldn't get a month's worth of.
But we know what you're saying, that we need that synoptic data.
Okay.
And so some fraction of the time is going to be devoted to these long-term, high-value data sets that many scientists will use for lots of different things.
Yes, so, there is a program for this long-term collecting data for historical kind of records, synoptic observations, like Jeff said. That is very important because snapshots of some little structures on the sun is not enough to understand the entire sun. So to understand the global processes, global generation of magnetic fields and global evolution of these magnetic fields, one has to do longer term observations.
Well, go ahead, Christian.
Go ahead. Okay, well, I go ahead, Tony. I think my question would probably come back better.
My question is about some of the science that DKIST is hoping to get to. I understand this conundrum, this dark energy issue that you talk about. When I first started at HAO, Hart Hundhausen used to have a fun question he used to always ask. We know that the solar photosphere is around 5,500, 6,500 Kelvin. Why is the solar corona 2 million degrees? And he would always ask that of everybody to try and get an answer. So that is one question that you're trying to answer. But what about this is a very, one of the things I love about solar physics is that it is a very practical research field, in the sense that what we understand happens on the sun affects us directly, and nowhere is that more true than with the study of coronal mass ejections and CMEs. What impact do you guys think DKIST will have on space weather forecasting, and in particular our knowledge of CMEs? When I left the field, there was still a big argument about whether solar flares were even related or causing CMEs. I don't know if that's been resolved yet, but what do you hope DKIST will help resolve with respect to CMEs?
So,
well, yeah, Jeff, you want to answer, or?
Well, I'll start. So it's related to the dark energy problem, that we know that, we know that the solar corona is heated by magnetic energy somehow. I mean, it may be magnetic waves, or it may be little tiny flares that create enough thermal energy to keep things hot. But somehow, what makes the corona so dynamic and so explosive is magnetic fields. But imagine we're in this environment where we're trying to explain everything with magnetic fields, but we can't measure them. Well, that's the big deal. DKIST and its coronagraph, coupled with its observations of the photosphere, is going to give us this revolutionary new understanding by directly measuring the magnetic fields that create the energy that changes the corona, that affects the Earth, the solar terrestrial environment that affects the Earth. So it's this, our hands aren't tied behind our backs and trying to build models, because now instead of just drawing the lines like cartoons where we think the magnetism is, we can go out and we can measure it. And that's a new thing. That's something that is
yeah. I want to add to this that what I said earlier, we will be able to see simultaneously photosphere, chromosphere, and corona. That means that we can measure magnetic field through all these layers, and we will see in dynamics how these magnetic fields are distributed, how they evolve. Plus, we'll have the possibility to measure velocity fields. So this velocity field, temperature, magnetic field will characterize the thermodynamics of these layers and the magnetic, what we call coupling. So how energy is transported from photosphere to the chromosphere and to the corona via magnetic fields and via waves, can be of different kinds, related to magnetic field and not related. So all this, it's all about energy transport. And then once we measure this, we know how magnetic field is distributed, how energy is transported. Then associating this with the events, activity events on the sun, we hope that we can understand how they are triggered, flares, CMEs, and so on. And Jeff correctly mentioned that right now, what models do is that they see magnetic fields in the photosphere, and then they extrapolate to the corona and the chromosphere in order to predict CMEs, in order to predict space weather. And that prediction is based on assumptions of that extrapolation. So now DKIST will fill in that niche, that missing element of the puzzle with measurements, and then prediction of CMEs will be more reliable, definitely.
So Svetlana, is it a lot like this, where in the past we've been able to see sunspots in white light? If you look at the sun through a solar filter through your telescope, you're looking probably at white light. You see dark spots. Those are one of the cooler layers of the sun. It's actually a little bit lower down. But when you look at that same area of the sun in the chromosphere, say H alpha, you're looking at a slightly higher region of the sun. You still see an active region, but it's going to look, you see a dark spot, it'll still look like a sunspot. But then when you look at these things in higher energies, you start to see magnetic active regions and filaments and all kinds of really cool things. Are you saying then that with DKIST, we'll be able to get a simultaneous picture of all of these layers of the sun at one time. So you could follow, let's say a flare goes off. You could follow that all the way from white light all the way up through H alpha through EIT. What is EIT? Iron lines.
Exactly.
Yeah.
Yeah. Exactly. So you will see how energy actually, when the flare starts, you will see basically at which layer the energy how to say, generated the most, and how it affects the environment, how the magnetic fields are restructured, and so on. And you can associate this with the triggering CMEs or other events, because you're right, we still, you mentioned that years ago we didn't know about whether CMEs are connected to flares or not, because we see both with and without. And it's the same question. We still don't know how CMEs trigger it exactly. So that is important. And that's what affects the space weather and predictions of the CMEs, from which active region we have to expect CMEs. That's a big deal.
Yeah, let's talk about space weather a little bit. First of all, Jeff, you want to give us a sort of a real simple explanation of what we mean when we say space weather?
So terrestrial weather is what the atmosphere and changes in the atmosphere, how they affect us. And space weather is a similar idea that the environment of the Earth out in space can affect the Earth, and it's dynamic. It changes. There's a solar wind, just like a terrestrial wind that emanates mostly from the sun. It blows particles. Those particles interact with the magnetism of the Earth in ways that, one manifestation of space weather that we don't see so much in Hawaii, but others throughout the world see is the aurora. The aurora is evidence that there are particles striking the Earth, and they're time variable, and they're even storms. They're rapid variations in the magnetism out in space created by the CMEs that you just mentioned that affect the Earth, and they affect things on the Earth down all the way to the ground. So over the last few decades, we've realized that as our technology depends more and more on satellites and the Earth environment out into space, we have to understand the space weather that's mostly created by the sun, because it affects the performance of everything from GPS to plane navigation to the power grid over large areas.
A question I get a lot, Jeff, and you guys can, and I don't know what this is, maybe just speculation, but is it possible for CMEs to be so powerful that they do, actually damage the grid? Can they actually do damage to electrons?
Yes, absolutely. And there were recent events when the grids were damaged in Canada and so on. They were recently not so powerful, but still powerful enough to damage ground-based equipment. But I want to bring the historical fact that it was a record. There is a record of solar flare killed a person on Earth. So that is absolutely recorded. So that was a Carrington event. Second half of 19th century. It was a very strong flare, white flare, what Carrington observed by eye, and then he put together that at that time it was already measurements of the magnetic field on the Earth. So the magnetic storm was recorded. Then later on it was found out that auroras were seen in the near equatorial regions by ships in the South America.
Wow, down in the equator.
Wow. They were spectacular. So the event was so amazing. We haven't seen anything like this in the 20th century yet. And at that time, it was teletype used for transmitting information, as you know. And so several people were shocked, got electrical shock by teletyping, all these things.
Yeah.
And one person was unfortunately killed even because the shock was so strong. Was killed. So that is the one historical record that the solar flare, killed a person on Earth.
Now, is it? I'm sorry to interrupt you. Is this the Carrington event, or is this before?
Yeah, this is the Carrington event.
Carrington event. Okay.
Well, describe what that is. You got to say what that is, Christian.
That was a big solar flare in 1860s, I think, something like that. Yeah. So, and it was white flare, which you could see by eye through the telescope. That's what he did. He saw like this white light increasing at the place where the active region was. We haven't seen that at all yet in 20th century.
Wow.
And if this happens now, then you can imagine that many satellites will be destroyed on the ground. Some power grids will be destroyed. So it's in a technological society that kind of event will be damaging, very damaging.
And
well, there was a Halloween flare about 10 years ago that was probably within an order of magnitude of the Carrington event.
Wow.
It didn't have the same effect because that CME and the flare were directed off to the side. So the sun produced this big outburst, and when it didn't come towards the Earth, it came off to the side. But estimates based on the number of X-rays and the particles that we detected from satellites suggest that might have been only 5 or 6 times weaker than the Carrington event. So it's a real thing, and there are astronomers now that we know that there's so many planets around other stars, folks are beginning to ask, well, could the flares in other stars be more powerful? And there are models that show that you could have a CME that directly affects the atmosphere. It produces enough. Basically, it blows away the outer parts of our atmosphere in a star that's a little bit more active than the sun.
Yeah.
Big CMEs.
On other stars, these white flares can happen pretty often. So this is not something exclusively here. It's there are stars where it happens regularly. Of course, not like every day, but can happen.
So the more we learn about our star, the sun, the more we can extrapolate what those effects might be around some other stars that may be more or less active than ours. For example, red dwarfs in their early life cycles and things like that, right?
More, yeah.
I just wanted to ask a quick clarifying question, Svetlana. You're calling these white flares. In other words,
Yes.
These were visible to the
yes
visible by eye through it via telescope, right?
Yeah.
So in the English language, those are white light flares.
Yeah.
White light.
They're the most energetic. Most flares are seen mostly in the light of hydrogen. We say H alpha, right? And they're observed all the time that way, or they're observed in X-rays.
Or calcium, yeah, you can say calcium lights. So most flares we see in chromospheric lines or coronal lines, transition region lines, but some you can see in this white light. It means that there is in terms of the spectroscopy, that there is also continuum is very powerful. So that is related to the energy of the flare.
Adam Synergy says that his ancestors' laptops were badly damaged back in 1859. So, yeah.
We do have a couple questions here. One is from Superluminal in the chat. He asks, or she asks, could solar flares be strong enough to be responsible for previous extinction events?
Yeah, that's a really interesting question. And so, particle events from, say, gamma ray bursters or other explosive events on other stars, we have a pretty good idea could be responsible for some events. I would put it this way.
Supernova explosions, yes, nearby.
Yeah, supernovas. It's hard to know how. Solar activity is something that we're all trying to understand, but we have this problem: is we only have a snapshot of how the sun behaves. And it's certainly true that there are some people that believe that major flare events, bigger than a Carrington event, could have had a significant effect on extinctions. And that's a subject of ongoing study. What would it take for the sun, for one of the mass extinction events to have been a contributor?
Yeah, we know that in the past sun was more active, and like a billion years ago scale, let's say. But it's also from isotope measurements, which go few millions years ago or thousands years ago. We also see that the sun was more active than it's now. Not like orders of the magnitude, but a little bit. And in those times, you see, in 19th century, we had a Carrington event. So a few thousands or millennia years ago, the events like this could be happening. it's not only particles, but it's also UV light, which is coming from those flares. And UV and particles are both very important for chemistry of the upper layers of the Earth atmosphere. So then the different processes, ozone layer, that's what we discuss also right now, how that affects ozone layers. It can be destroyed for some time. And it takes time to recover this ozone layer after elimination. So that kind of minor effect on the atmosphere, destroying the ozone layer, could affect the life on the Earth, which is could be sensitive to UV radiation.
Yeah, we went through that with the ozone hole too, didn't we? I want to talk a little bit about the data that's going to come off of the telescope. So what are the plans? So as I understand it, when DKIST is commissioned and is starting to take images, you guys are going to have something like a time allocation committee that goes over proposals, right?
Yep.
And then based on those proposals, you'll decide who gets observing time, and then will the astronomers that are the principal investigators of that proposal, will they get the data directly, and then will it ever be made available later? What's the plan? What's the data plan, I guess?
So this is funded by our tax dollars, which means that data belongs to you. And most of the data comes in a format which is hard and difficult to interpret and takes a lot of tools to make sense of. But the data fundamentally is public, and the only discussion about how it isn't public is how long it's in the hands of just the scientists that organize the data. But there's no question that all of the data that comes from this telescope is publicly available, and it's just there may be a period of time where the scientists that designed the particular observing program have access to try to take the first cut at trying to interpret it. And that proprietary period might be 6 months. In the case of a student who's doing a PhD, it could be a year. But in general, the answer to your question is it's public. And for the kind of data sets that we talked about, the legacy data, right, the things that happen every day that are the long-term, high-value, multi-purpose data sets, that data will be public as soon as it's analyzed and available.
So there's kind of two components to it. There's the right-of-way data set, and then there's more embargoes only because you want to give the investigators time to write their papers and do their dissertations and things.
I think that's kind of like the Hubble Space Telescope, right?
Yeah, it is. It's
Exactly.
They're embargoed for a year usually, their data. So
are you gonna? Yeah, I was surprised when he said 6 months. That's a fairly quick turnaround.
Very short, yeah. I'd like to add a little bit that DKIST actually organizes a data center which will be serving this data in this particular format, very convenient and with pipelines and so on. And maybe I would like to add that role of our institute in Germany, that we contribute one of the first light instruments to this telescope, and we also collaborate with the data center to maintain the data for astronomers, for basically for US, of course, first of all, astronomers, but maybe later on for worldwide astronomers.
So are you guys running the data pipeline too, Svetlana, or just this one instrument?
Yes, we are developing one instrument and pipeline for these instruments. We deliver this for everybody who will use it, and we will maintain the database for this instrument. Basically, that's our part of DKIST and all DKIST.
But the data center that the Kiepenheuer Institute maintains is primarily a portal to the data in Europe.
Will be, yes. When the data policy is defined for European usage, it will be. But we will be running pipeline and providing the calibrated data for DKIST community. Yes.
Okay. Well.
For our instrument, yes.
All right. Well, I think we're going to have to stop it there. We've only got a couple of minutes left, and so guys, my Facebook poll failed. I was watching Facebook this entire Hangout, never saw how you could vote in it. So I created it, but it did. Facebook is like that. It's like, I don't know. I made it. So how do people interact with it? So Obviously didn't push the right buttons. This is going
Yet another reason to delete Facebook right there. If they can't get the poll right, the heck with it.
Well, I guess I'm having a
they
bit
can
of
have all my personal data, but if they can't do a poll, then
yeah, really. I mean, come on, man. So the answer, though, let me give you the answer to the question. It was option 3. The solar significance of the highway leading to Sunspot, New Mexico, is that it is called New Mexico Scenic Byway 6563, which is the wavelength in angstroms of the hydrogen alpha line. So that is the.
Do you know which scientist proposed that back in the 50s and 60s?
I don't. Who was it?
Did you know George Simon?
No, I never met him. A bit before my time, I think.
He was an early solar physicist who was he was there with Caltech with Bob Layton and worked in the early days and things like that.
Good. I love it up there. It's so peaceful and quiet. Apache Point is really just down the road. They took the Sloan Digital Sky Survey data. It's an amazing place to go. You can visit this facility. It's still up. It's not being run by the National Science Foundation anymore. It's being run by the New Mexico State University. It's a cool place to go. If you're in Boulder, lots of cool solar places there. If you're in Hawaii, there's even more. Jeff, if you go to Maui, I'm not volunteering you for any personal things, but can people go to Haleakala and see things, or is it off limits?
Well, we don't have the visitor facilities that for example Sunspot has,
or Mauna Kea, I suppose,
or Mauna Kea. They have a visitor center.
Yeah.
But you know, if people have a you can go to the crater, you can go to the summit, you can look from the national park system publicly. And we're always trying to facilitate interested folks through our own efforts. When it works out, we often take groups up there and show them what we're doing. But the answer to your question is we don't have a formal a visitor system.
That's also true of Mauna Loa. Do not try to go to Mauna Loa.
Oh yeah, I mean, can you imagine hundreds of cars driving that road to Mauna Loa?
All it is, folks, is a single lane road with a paint can. They had a paint can, a white can, a can of white paint, poked a hole in the bottom, dribbled the paint up the road. That's your only marker. Do not try this unless you are a professional. But you can't go to Mauna Kea. Mauna Kea has a visitor center. You can't take rental cars up there, though, I'm told. So,
well, on Maui, one can drive to the summit, which is allowed for people to visit.
Mm-hmm.
And from summit, you can see down the observatory. So you cannot visit observatory, but you can see it from the top. It's very nice.
Great.
Well, when is first light again on DKIST? When are you anticipating that?
Well, so first scientific light is now sometime actually in 2020. It's towards the middle of the year, but this is where the middle, where the rubber meets the road, and all sorts of things are going on, and the schedule is getting moved around as the optics come into place and the instruments and all the different bits. So that could change, but the first official first light for the telescope, first scientific light, is probably something like the summer of 2020.
Okay, well, great. Well, then, if you need a little PR for that, we can come up to Tony and I will come up to the mountain and
live stream for first light.
We'll live stream from the summit.
Yeah, that's a
So
great
like
idea.
all 5 people within LTE range can hear us.
There you go.
All right.
Yeah, that's a great idea.
Cool. All right. Well, guys, I hope you'll come back. Give us some more update on DKIST
Yes,
as time approaches. Also, I want to have you back to talk some more about ELF, which is also a ground-based observatory. We talked about it before, but I want to talk about it again. So I hope you'll come back and talk about those two also on our Telescope Talk Pro Hangout. Okay, folks. Go ahead.
No, just a question. I wanted you to say a little bit, just one sentence about this new series that you have, which we're now part of. This is a bi-weekly about astronomical telescopes and facilities.
Yeah, there's 2 components to it. There's Telescope Talk Hangout. Now, on one week, I talk about amateur astronomy, what telescopes to get, what are good buys on amateur astronomy, should you build your own observatory in your backyard, stuff like that. The other week is the pro version. That's what we're on now. This is where I talk to professional astronomers working at ground-based observatories to talk about the discoveries that are happening on ground-based instrumentation from around the world. My other hangouts that I do on Thursdays, those are sponsored by the American Astronomical Society, and so it tends to be very American-centric. I wanted this hangout to be very international. For example, in 2 weeks, I've got Hector Socas Navarro on from Tenerife, who's going to talk about the Canary Islands, and we're going to talk about Clark exobelts and things like that. So that is that's sort of what we're doing with these hangouts. So, and because ELF, what you're working on with Planets Foundation, is also important and ground-based, it also fits in with this hangout series. So that's what it is.
Cool.
All right.
Okay.
All right, folks.
Great. Thanks for having us.
You're very welcome. Thank you, Svetlana. And
appreciate it.
before you leave, I just have to sign off, and then you can go. So I want to thank you all so much for watching, and as always, keep looking up. And then I lose my cursor. Okay. Well, we're off. So there you go.
All right. Good show,
Keep
everybody.
looking to the sun.
You know, we're only half joking when